Hi everyone, this is Mr. Smith talking chemistry again. Today we're not going to talk about neutral atoms as much as we're going to talk about ions when protons do not equal electrons. Here we have a very simple atom here, number 1 on the periodic table, kind of the simplest, easiest, 75% of the universe type of atom. 1 proton, 1 electron. Atomic number down low, that matches the 1 proton we have. The mass number is protons plus neutrons, so that's up top. I can add some neutrons to it. Now I have 2 particles in the nucleus, so I have a mass number of 2. And I can keep adding, but it's still, add neutrons, still a neutral atom. What will change this from not being a neutral atom anymore is this proton to electron ratio. The 1 red proton in here and the 1 blue electron out there in orbits. Now electrons can travel in orbits, that's in orbits like planets around the sun. That's a bit more figurative. What's more truthful is actually this electron cloud, which we'll talk about in a later unit, but for now, orbits does well for us. So 1 proton, 1 electron, that's your definition of neutral. But what happens if you add another proton? Well, on the periodic table, when you add another proton, you get a new element. That element is going to be number 2 on the periodic table, helium. Now I have an unequal amount of protons to electrons. 2 protons, 1 electron. 2 protons, 1 electron. So that gives me an ion. It is now charged. There are now more positives than negatives, and that's what this little chart over here is showing. Blue positive, red negative. This is tilted towards, I think I said that incorrectly, blue negative, red positive. This little needle is pointed more towards the positive sign because there are more positive protons than negative electrons. And so this is no longer a neutral atom, but instead it is called an ion. And specifically, it's called a cation. Now to make it neutral, add in the second electron, and it is now neutral. Notice the charge goes not bottom left where the atomic number is, not top left where the mass number goes, but now it goes top right. Typically you don't see the 0 here, but to kind of show off ions and charge, we're putting a 0 here. But as soon as you have an unequal proton to electron ratio, for example, add in an electron here, and we'll talk about how it is now on the second energy level, the second orbit. Now we have 3 negatives to 2 positives. So overall, there's a -1 charge. So where does that -1 come from? Well, it comes from 2 things, the negative and the 1. So the negative comes from the fact that there are more negatives than positives. How many more? 1 more. So the more negatives makes it a negative symbol here. And the fact that there's 1 more negative than positive puts a 1 here. If I would add in another electron, now we have 2 more electrons than protons. I have 2 more negatives than positives. So now I have myself 2 negatives. Now I can neutralize this. Neutral the charge. Now I have 4 protons, 4 electrons. Notice it's no longer helium. I switched from helium, 1 extra proton gave me 3 protons, to lithium, and now I have my 4th proton in there, which is beryllium. So my 4 down there has changed, my atomic number has changed to 4, and now my charge is back to neutral, and my total here is a neutral atom. Now beryllium actually prefers to lose a couple of electrons, so I'm going to take these 2 away. And now we have a +2 charge. So it's +2 charge for a couple of reasons. Again, the positive because there's more positive protons than there are negative electrons. And the number 2 is because there are 2 more positive protons than there are negative electrons. And this number up here, the symbol and number here up here, is a running tally of how many extra protons versus electrons there are. So it's the 2 plus does means there are 2 more protons than electrons. There are 2 more positives than there are negatives. Notice this mass number up here doesn't change no matter how many electrons I add. That has changed down to +1. This is now still 7, added another one. Now it is neutral. Now it is neutral. Still 7. Electrons contribute so little mass, they're not factored into the mass number of pi. Now beryllium has 5 electrons versus 4 protons. So for the electrons, there is one extra negative particle that's not matched with a positive particle. One extra negative, and that's what this -1 means here. It can also be written 1 minus or -1. And we can keep doing that for as much as possible. So to neutral this out, I'm going to add in, for now I have 7 electrons, if you can kind of count them all, 2 on the inside, 5 on the outside. How many protons do I need to balance out 7 electrons? We said 7, you're correct. What's the name of an element that has 7 protons? If you said nitrogen, you are correct. My atomic number is 7. Again, you can kind of count them up here. It's kind of tough to count the big blob of red protons, but up here there's a nice little, almost of a histogram here. 7 protons, 7 electrons. It is now neutral. Now nitrogen actually tends to prefer to have 10 electrons. So let's put them there. Used up all my electrons. So now it is a negative ion. That picks up the vocab anion. A-N-I-O-N. And so notice we have a -3 charge here. Again, there's 2 parts to that. The sign telling you there are more negative electrons than there are positive protons, and the number tells you how many more. In this case, I have 3 more negatives, and that's why it's a -3 up there. Again, notice the mass number is not really relevant here. How many neutrons aren't relevant to the charges because neutrons are uncharged. Now, how many neutrons are there matters in a different context. It matters for nuclear chemistry, so only having 3 neutrons is not good for nitrogen. And so when we do nuclear chemistry, we're going to keep on having just the right number of proton to neutron ratio for it to be radioactively stable, nuclear chemistry stable. But again, that's totally different than what's happening out here with the electrons. You can take away every bit of neutron, and that doesn't change the charge at all. It also doesn't really change the fact that nitrogen wants to have 10 electrons. Nitrogen is going to form this -3 charge most often. In fact, many elements have this preferred charge. And so you have this periodic table here. You have this one here that we've been using in class. And then this one is what's going to come next. The periodic table is very well organized. It turns out it's organized by charges. So the scientist who organized these was a man named Dmitry Mendeleev, who does get an element named after him, 101. He organized them by chemical and physical properties, similarities, by atomic mass. The fact that we go from 1 to 118 in some type of increasing order is not a coincidence. The charges, though, that was unknown at the time. That first column that I have labeled, that I've kind of hand highlighted red, all those ions are there forming +1 charges, or 1+ charges. The second column really likes to have 2 charges, 2+ charges. So we're going to talk about this later on, but the periodic table does give you quite a bit of depth in terms of the preferred charges, in terms of gaining and losing electrons. So magnesium has 12 protons, and while neutral has 12 electrons, but magnesium prefers to only have 10 electrons. And so when 12 electrons become 10 electrons, you still have 12 protons. And I can do that over here a bit better. All right, so here's another way to show this off to you. I'm going to pause this so they don't move around so much. Although, again, electrons are moving actually quite fast. But I'm not going to show that off to you. So there you go. So we have the protons and neutrons in the center. The electrons are outside of the nucleus, not quite orbiting like planets around the sun, but they are outside of the nucleus. And here we go with magnesium. And now, for reasons that we'll talk about later on, it turns out that magnesium is going to form a +2 charge. Now, why is that? Because magnesium likes to have 10 electrons. It's the most stable when there are 10 electrons. And so let's take a couple of electrons away. So now I'm down to 10 electrons, and magnesium is going to form that +2 charge that's there. And again, this time it's written 2+. This is actually more common to write it this way with the 2+ charge there. And so that's how most of this, all of the second column works. It's going to get rid of 2 electrons. So this is something to refer to pretty often. It's fairly random, the 1, 2, 3, and then 3, 2, 1. These atoms like to tend to gain electrons, and we'll talk about that. This family over here, they're called nonmetals. All of this stuff here that forms positive charges are called metals, and there is some middle ground there is the gray area, which we call the metalloids and the semimetals. But for now, you're going to kind of keep seeing these patterns, and we're going to make use of these patterns later on, especially when we do something called ionic bonding. But for now, we just want you to be able to kind of take away and add protons and electrons and be able to either generate the charge, or if you have the charge, to go ahead and generate how many protons and electrons are there. So good luck with your practice. Thank you for your time. And remember, chemistry is everywhere.